right, so we'll get to the question in just a second here. Does anybody know what language in the world is spoken the least?
What did you say?
What language in the world is spoken the least? Good guess. Sign language. Awesome. Yep. Because it's quiet. Anybody here ever been to a mountain?
Yes.
Nice. Which one?
Mount Emma.
Really? Where's that?
Colorado.
Interesting. Did you get to the top of it? Sweet. One of the neat things that I'm sure Bree knows, and I for sure know, mountains are actually really, really funny. In fact, they are hill areas. Happy Monday. Okay. So let's take a look at this question here. Nobody in my other physics classes have been able to figure this out. So if one of you guys can take this down, you get brownie points, and I will hold it over both of their heads tomorrow. So we've got a graph here. It's force versus distance. The question is, what does the slope mean? We've done this sort of thing in the past. Anybody figure out what that slope actually means without me giving any hints? Caroline. That is true. The more you compress the spring, the higher the distance, the more force it takes to do that. But if we could put this slope in, like, there's something we've talked about that we would call this slope. Like with the position time graph, the slope was velocity. For the velocity time graph, the slope was acceleration. Yes? Okay. There's no pressure because nobody's gotten this yet. Nope. Nope.
Energy.
Not quite. What would the units be? Can you figure that out from the graph?
No.
Rise over run? Newtons per meter. And what do we know that's newtons per meter? Nope. Nope. The K. There we go. Yep. So the slope of this line represents your spring constant K. So if you had 10 newtons and this was 5 meters, your spring constant would be 2 newtons per meter, rise over run. So that's one way that you can determine your spring constant. It measures the strength of the spring that you're dealing with. So, okay. That's a real easy one to put into a multiple choice question, so make sure you get that written down. So let's take a look. Worksheet number 3. You've seen the answers. You've tried them all. What should we talk about?
8 and 9.
8 and 9. Gavin, do you have another one? 4? Okay. So we'll do 8, 9, and 4, and then we'll see what we want to do from there. So number 8, we've got a bullet being fired from a gun with a barrel that is 85 centimeters long. The average force exerted by the expanding gas is 5,500 newtons. How fast will the bullet go? So we're looking for velocity. And there's only one equation in the ones that we've looked at for this section that has velocity in it. Of course, that is kinetic energy. So kinetic energy is definitely going to play a part here. And, it looks like it's going to be the last thing that we use because at the end, the bullet is moving very quickly. So the final energy here is going to be kinetic. Bless you. Now, the bullet starts in the barrel of a gun. And so it's at rest in that barrel. It has no potential energy. It has no spring potential energy. And it doesn't have any kinetic energy. So what the gun has to do is it has to perform work on that bullet to get it moving. So this equation is going to be work equals kinetic energy. So if we wanted to try and figure out the velocity, let's just put this into the equation it would be. Again, work is also change in energy, but we don't, change in energy would just be the change in kinetic energy, and that's not going to get us any closer to our final velocity there. It gives us specifically the force So that's kind of your hint to use this equation here, force times distance. So if I want to solve for velocity, I'm just going to isolate it, multiply both sides by 2, divide both sides by m. And because that's equal to v squared, I am going to erase the square, but then I got to square root the other side and then plug in those values. The force is given to us as 5,500. The distance is 85 centimeters. How many meters does that come out to be? 0.85. And then the mass is given to us in grams. We got to convert that too. When you're in grams, to get it to kilograms, you divide by 1,000. So your mass would be 0.01 kilograms. So then it's just a matter of plugging those in. Out pops your answer. And your final velocity. This is booking it, by the way. I mean, this is faster than the speed of sound, if you remember from that section. Questions on number 8. Trickiest part about 8 is probably the conversions, but you do have to be aware that if they give you a force, they're really hinting you got to use Fx for work and set that equal to your energy. Okay. We'll also do number 9. I think I want to do number 10 too, just because I like Wile E. Coyote. So number 9, this one looks tricky. It's not as bad as you might think. So number 9, we've got this little kid going down a 5-meter high slide, reaches the ground with a speed of 2.8 meters per second. That's pretty slow. Must be a pretty crummy slide. How much energy, or maybe it's like one of those sweaty summer days where you try to go down the slide and you just get stuck halfway? Maybe it just happened to me. Did they make metal slides when you were kids, or were they all plastic?
I have metal slides.
Okay, yeah, the metal ones. Yeah. Those are the ones I'm thinking of. Oh boy, yeah, those babies burned, and they hardly got you where you wanted to go. So this must be a metal slide here. And so here's the thing. At the top of the slide, this kid only has potential energy. At the bottom of the slide, this kid only has kinetic energy. So it's a pretty clear transfer from one to the other. Now, when it talks about energy being lost, you're kind of tempted to think of friction and how can I incorporate force of friction and heat into all this. But it actually gives you enough information that you can solve for both of these two things. So if you can solve for the potential energy at the beginning and the kinetic energy at the end, all you got to do is take the difference, and that's how much energy was lost. So potential energy, mgy, so that's going to be 24 kilograms times 9.8 times the height of 5 meters. And that comes to 1176. As far as the kinetic energy goes, 1/2 mv squared. Two point eight, yeah. And you plug that in, you get 94.1. So you've got both of your energies right there. So all you got to do to find how much energy was lost is take the difference. That looks like it comes to about 1080 or so, if we're rounding to 3 digits. And that would be number 9. Further questions on that one? Okay. Let's take a look at Wile E. Coyote. I actually have a DVD that is only Wile E. Coyote and Roadrunner cartoons. That would be a good physics thing to bring in, I think. So, letter A, probably don't need to do that one. So he's shot out of a cannon going straight up, and he's blasted with a velocity of 50 meters per second. And it gives you his mass. So in order to find out how high he's going to go for letter A, all you do is you take the kinetic energy he had immediately after he was launched out of the cannon, and you set it equal to the final potential energy he'll have when he eventually comes to rest momentarily at his maximum height. So, you would set those two things equal to each other. You have all this information except for the height, so you would just solve for that height y. Your final answer would be 128 meters. So, and the cool part too is the masses cancel. So 128 meters for letter A. Letter B is the tricky part. Now it says he's lost 20% of his energy due to air resistance. So he's really launched fast out of this. And that's true. I mean, 50 meters per second is about 100 miles an hour. So he's screaming along, losing a lot of that energy because he's being pelted by all this air as he's blasted out of that. I mean, imagine being at 100 miles an hour and you stick your hand out the car window. That's a lot of force and lots of energy being lost. So if you lose 20% of your energy, then what you have to do is you have to compensate for that right at the beginning. And of course, if you lose 20% of your energy, you still have 80% of the original energy. And of course, 80% is the same thing as 0.8. So that's how you would modify this equation then. So yeah, divide both sides by g. You'll get an answer that's a little bit less, 102 meters for letter B. We'll carry this one through. So let's see here. 0.8 times 1/2, I believe, is 0.4. And the velocity was 50. And if we want to set that equal to the height, we got to divide both sides by g. So when we plug that information in, yeah, that's going to come to 102 meters, which is awfully high. 300 feet, that's about a football field in height. Further questions on number 10? Okay. We'll assume he got the Roadrunner here. Number 4 I heard as well. So let's take a look at number 4. So I can see where this one would be tricky too here. So it gives you the mass and velocity that the bullet has originally. So that means we know its original kinetic energy, which is nice because that's what all of its energy starts as. Now it eventually goes into the wood and comes to a stop. So what's going on here is the bullet is doing work on that piece of wood. It looks like the block doesn't move anywhere, but it's still doing work on it nonetheless. And that ends up coming out as heat. But if we want to figure out how far in that bullet's going to go, we know it starts with kinetic energy, and at the end, all of that energy is transferred out of it because it's doing work on the block. And again, this is another one where it kind of hints for you how to handle this because it tells you exactly what the force is. 50,000 newtons is being applied on that block. So we're going to use force times distance. And if we want to solve for distance, we divide both sides by the force. So this is the same thing as saying 1/2 mv squared divided by force. And that's equal to your distance traveled there. So we can just plug those little numbers in. Oh, this is another one where we got to make sure that we convert to kilograms. So 25 grams divided by 1,000 is going to be equal to 0.0 0.25 kilograms. Original velocity, 350. And the force is given as 50,000. So that's what you'd have to deal with there. Your answer is going to end up being 0.0306. And that's number 4. So yeah, you start with all kinetic energy, you end with no energy, and where that energy goes is it goes into heat. You know, usually we think of work as adding energy to the system, and that's really what's happening here. The bullet is adding energy to the block, and it comes out as heat, which we usually think of as energy loss. But if you want to just try and remember something quick here, if it ever gives you a force, you're going to have to do this. You're going to have to put that force to use. All right, those were the ones I heard. What else should we talk about? Number 5. Yeah, that's another favorite. So we'll do number 5 in its entirety, but rest assured you're not going to have something like this on the test. So either way, it's kind of a fun little way to remember the good times when there was a lot of snow on the ground and we were doing force diagrams. So let's take a look at number 5. This guy is pulling this block to the left at a 30-degree angle. So that's what's happening to the block right there. Of course, if we're going to put that force on there, we got to make sure we put all the other forces. Gravity on the box is going down. It's got a normal force going up. That normal force would be smaller than usual because he's already pulling up a little bit, so the table doesn't have to exert as much effort to keep it from falling through. And there's friction. There's our fancy force diagram. So that's all we would need for letter A. Letter B, how much of the force acts in the direction of the motion? I suppose I should label this one. This is our tension force. It tells us that it's 100. So if we're looking for the tension in the x direction, the force acting in the direction of this thing's motion, the motion is horizontal, so that means we got to find the horizontal portion of this 100 newtons, which is what it's asking for right now. And you can solve for that because you know how to deal with triangles. So if I wanted to figure out what this side of the triangle is, it's the adjacent side of the 30-degree angle, which of course means we got to use cosine. So tension in the x direction is going to be equal to 100 times the cosine of 30 degrees. Because we always use cosine when we're dealing with the adjacent side. And when you put that into your calculator, you get 86.6, as long as you're in degree mode anyway. So again, this is the force that's acting horizontally. Now, I didn't have you just do this because I wanted to exercise your brain. You need this number because remember, for the second part, when it says find out how much energy is transferred via work as the person pulls this thing, work is equal to force times distance, but But we're not going to put 100 in for this force, because this force is however much force is acting in the direction of the object's motion. So it's moving horizontally, meaning this is actually the force in the x direction, which we just calculated. And the distance is 10 meters, so I'm pretty sure that comes out to 866. And remember, work is the same units as energy, which is joules. That's letter B. Are you guys ready for letter C? All right, let's dive in. Letter C. So it says, find out if the box moves at a constant speed. What does this say about the kinetic energy of the system? So we can't answer the second part till we answer the first part. Now, if this box is going to, whether it's speeding up or whether it's not going to move at all, we have to look at the forces that are acting horizontally. So we know this tension in the x direction. That force is 86.6. What's going to happen to this block if the force of friction is the same value? Is it going to go anywhere? No. No, it's not going to go anywhere if these two numbers are the same. We got to figure out if he's actually getting this box to move or not. So if that's the case, what happens if this number is, 86.6, and what if this one's 60? Then what happens? Yeah, then it moves. It speeds up because this force is bigger than that one, so that means it's going to accelerate to the right. So that's really what we got to figure out. We got to figure out if this force here is bigger than the force of friction. That means we got to figure out the force of friction, which turns out to be a big chore. We're going to do it anyway. So force of friction is coefficient of friction times normal force. Easy enough. We know the coefficient of friction, I hope. Yes, we do. Yep, 0.15. So now we just got to plug in the normal force. Ain't nothing easy, is it? So if we want to figure out the normal force, we got to do a force equation. So we'll do that right now. And again, this isn't the sort of thing you got to study up for on the test. So going up, all our forces include normal force and tension in the y direction. Going down, we've got gravity. The object is not levitating up or down, so that's all going to equal 0. So if I want to solve for normal force, I'm going to throw these two jobbers on the other side and figure out what they are. What's that? That's right. So force of gravity becomes positive when it moves over. Tension in the y direction becomes negative. So now it's just a matter of finding these two values. Gravity is easy enough. That's just mass times 9.8. But tension in the y direction is a little bit more difficult. So tension in the y direction is going to be this thing. Yep, exactly. So this is FTY, and it's the same thing as this, except it's a sine. And when you do that, you end up with 66 newtons. Wait, 440 newtons. So 440 newtons is going to go right there. Force of gravity is going to be 50 times 9.8. So that's 490. So then we just got to subtract those two. So 490 minus 440. And we're going to get 50 for our normal force. So then 50 newtons goes in here. Coefficient is 0.15. Ah, shoot. I did something wrong. I read too far ahead. So 440 does not go here. Should have just done the calculation instead of looking ahead at the answer. That's what I get for cheating.
100 sine of 30 is
50? Okay, thank you. So 50 goes here, which means 50 goes there. So 490 minus 50 is 440. That's where that 440 comes from. Yeah, there we go. Thank you. So 440 times 0.15 gives us our force of friction, which 66, absolutely. So what's happening here? Is this box moving or is this holding still?
moving.
It's moving, because force of friction is less than the tension in the x direction, which was 86.6. And what then does this say about the kinetic energy of the system? Any thoughts? Yeah, it's increasing. It's going up. Yeah, the work is going to be increasing. So, yeah. And in terms of letter D, it says here energy is added to the system through work. Which energy transfer is larger? So the energy transfer of work going into the system is larger, as Solomon was saying, because it's speeding up. So more energy is going in through work than is going out through heat and friction. So, alrighty. Any last questions on this? All right, I'm going to come around and grab that from you then.